All right, friends, this is a re-recording of the 9 o'clock lecture for February 7th. It turns out that somehow in class I didn't click the record button properly, and therefore the lecture wasn't recorded. Last time we were talking about the Aldol reaction, which, as you recall, is the reaction of an enolate with a carbonyl compound. In this case, it's a self-aldol reaction, and the intermediate, we form the enolate with OH minus. The intermediate that's formed, the tetrahedral intermediate, has a negative charge on the oxygen. At that point, we ask, do we have a good leaving group? And the answer is no. So we wait until we wait, and then the negatively charged oxygen gets protonated by water, and we get to our aldol product, which is a beta hydroxycarbonyl compound, or alternatively, we go on to do the elimination reaction and get the alpha beta unsaturated carbonyl compound. And just to clarify, this portion of the molecule comes from the enolate, and this portion of the molecule was our electrophile or ketone. Today we're going to introduce a new reaction called the Claisen reaction, but you shouldn't think of it as a separate thing. In fact, it's just the ester version of the aldol. What do we mean by this? Well, if we take this ester and react it with sodium ethoxide, which is just sodium ion and the ethoxide ion, we're going to form a small amount of enolate, because the pKa for the ester alpha proton is so much higher than that of ethanol. We'll form a very small amount of ester enolate, just as we formed a small amount of ester in the aldol reaction. And then this enolate will attack another molecule of ester that's so far not been deprotonated. That attack generates, as we saw in the aldol reaction, a tetrahedral intermediate with a negatively charged oxygen. And just to be clear, we'll use the same labeling scheme. Now, as we compare that tetrahedral intermediate with what we had above, the difference is in the aldol reaction, there was no good leaving group on the now beta carbon, right? Whereas in the case of the Claisen reaction, or the ester version of the aldol, we do have a decent leaving group, at least a decent leaving group relative to the negatively charged oxygen. So basically we're comparing these two groups, and we're asking the question, is it reasonable for these electrons to kick down and for ethoxide to leave? Of course, if that happened, this would be the product that we get, but ethoxide would have been the leaving group. Now, you've learned in 351 that ethoxide isn't a particularly good leaving group, but the comparison we want to make is between ethoxide here after it has left and the negatively charged oxygen in the tetrahedral intermediate. In this case, we're asking, are they of similar reactivity, similar stability? And if so, then this step should be reasonable. So remember, a negatively charged oxygen can kick off another negatively charged oxygen leaving group. Now, this ultimately is our Claisen product. Unlike the aldol, it's not a beta hydroxy carbonyl compound. Instead, it's a beta keto ester because we have a ketone on the carbon that's beta to the ester. In practice, and so I'm fine actually if you want to stop the mechanism here, though your book points out something that happens and it actually explains why this reaction is irreversible. So keep in mind, and I will just show you this for your enrichment, you wouldn't have to show this mechanism, but keep in mind that a proton alpha to 2 carbonyls has a unusually low pKa of about 13. So as soon as negatively charged ethoxide leaves, likely the first thing that happens is an extremely downhill irreversible type step under these conditions where we remove the alpha proton and form the enolate. And then it's only upon subsequent aqueous workup that we are able to reprotonate our stable enolate to give us our beta keto ester. And essentially we do this by adding water and adjusting the pH until it's lower than the pKa for this proton. So some ask, why do we deprotonate then reprotonate again? That's simply a practical issue reflecting the fact that when ethoxide leaves in this step, it's a good enough base to remove that proton that's alpha to 2 carbonyls. But in terms of, show me the mechanism, you could stop here. All right. The Claisen reaction, this is a self-Claisen reaction that I've just shown you. Of course, sometimes we will want to do the cross-Claisen, and the cross-Claisen where we were using one ester that we want to be the enolate and the other to be the electrophile has the same issues as the cross-aldol, and so we can approach it sort of similarly. One way is to use as your electrophile an ester that has no alpha protons. So since this is our electrophile, we'll label it purple. And then we'll use as our nucleophile this ester that has just one kind of alpha proton. We'll use sodium ethoxide as our base. By the way, we're using ethoxide as our base, and we're matching the identity of our base to the identity of our ester, because if ethoxide as a nucleophile attacks the carbonyl carbon, we'll have this tetrahedral intermediate with 2 of the same leaving group on it, and whether one or the other leaves, you just go back to the same product. So matching the same starting material. So matching the base with the ester ensures that any undesired attack of ethoxide on the carbonyl carbon is inconsequential. So here's the molecule. It's going to become our enolate, and the desired cross-Claisen product would be this beta keto ester, where this is the new bond that we made, and it's the cross-Claisen product. Now, you would still worry about self-Claisen of the ester, the orange ester with itself, but I will allow you to pretend like this isn't an issue, and that if you use an ester partner with no alpha protons, that the reaction works well. Another another example of a cross-Claisen would be to use an especially reactive electrophile. So and I'm not even sure how we pronounce the name of this molecule. It is an ester, but it's also sort of an acid chloride, and it also has no alpha protons, so it must be the electrophile. And we'll use the same ester as our nucleophile. We'll use sodium ethoxide as our base. We'll first make the enolate, which I'm not going to show. I'll just draw the enolate and then show it attacking the reactive electron-poor carbonyl carbon. The tetrahedral intermediate looks like this, and it's very similar to the tetrahedral intermediates we drew for the Claisen examples above, except for the fact that now we have two good leaving groups attached to the carbon of the tetrahedral intermediate, and we're going to have the oxygen kick off the best leaving group, which here is Cl-. And you can tell that Cl- is the best leaving group because its conjugate acid HCl is so much more acidic than the conjugate acid of ethoxide as a leaving group, which is ethanol, pKa of 16. Interestingly, this process allows us to make a molecule you've seen before. This molecule is called diethyl melanate, and it's a molecule you saw in chapter 17 as we dealt with enolate alkylation in the so-called malonic ester synthesis. This is how we prepare diethyl melanate. And recall, this is a convenient way to generate alpha alkylated carboxylic acids. So it would be useful for you to take these two starting materials and figure out how to get to the following carboxylic acid. I will write the answer to this synthesis problem in the notes when I post them, but don't peek at it. Give this a real try. This is a very nice sort of way to integrate what we're learning now with what we learned in a previous chapter in the form of this synthesis question. All right. As with the aldol, there is an intramolecular version of the Claisen reaction. It has a name, the Diekmann condensation, that, but we'll just think of it as the intramolecular version of the Claisen. The idea is that if I have a diester with the right number of atoms between the esters on either end of the molecule, and the molecule I've chosen is symmetrical, so we don't have to worry about whether this alpha proton comes off or this alpha proton gets removed by our base because they're identical. In any case, the first step is going to be our base removes the alpha proton. That generates an enolate. The negative charge on that alpha carbon. And now it's useful to count carbons whenever you're going to make a ring. I'm going to have this negative charge on the alpha carbon, that enolate, attack this carbonyl carbon to give me a tetrahedral intermediate. And now I'm going to count how many atoms are in that ring. 1, 2, 3, 4, 5, and 6. So if I've just made a new ring, what I do, after counting the atoms, there's 6 in the ring, so I'm going to draw a hexagon, and I'm going to number the atoms of that ring. The new bond I make is going to be between atoms 6 and 1. Atom 6 should have a negatively charged oxygen and the ethoxy leaving group. Atom 1 should have the ester attached to it, and that's it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 with the new bond between 1 and 6. So we've made this 6-membered ring, and then as we saw above for the Claisen reaction, electrons kick down and leaving group leaves, and that should give us a beta keto ester. So we'll show that happening here for this intramolecular reaction. Electrons kick down, leaving group leaves. And your product is this beta keto ester. Okay. All right. So one of the skills that's going to be useful for you in this section of the class is structural patterns. Learn to recognize this beta hydroxycarbonyl compound as an aldol product. Learn to recognize an alpha beta unsaturated carbonyl compound as an aldol product. Learn to recognize the beta keto ester as a Claisen product. Learn to recognize a beta keto ester in the context of a ring as a Claisen product. So why worry about the Claisen reaction? It turns out that biology has a version of this Claisen reaction that's pretty important in the synthesis of long-chain fatty acids. In the previous unit, we talked about ester hydrolysis, or under basic conditions, or the saponification reaction, where we hydrolyze the ester linkage between glycerol and the fatty acid that's present in the triglycerides, or fats and oils. So now we're going to talk about how biology actually makes those long-chain carboxylic acids. And it involves a Claisen reaction, and this is described in your book. But it doesn't involve esters. It instead involves a thioester. Okay, thioester is the sulfur version of the ester. And thioesters are more reactive than esters because a negatively charged sulfur is more stable than a negatively charged oxygen because of the size difference between the two. And this is reflected in the fact that an alcohol has a pKa of 16, whereas the corresponding thiol has a pKa of 8. So Sr minus is a much better leaving group than Or minus, which means the thioester is more reactive than the ester. Okay? So nature doesn't use acid chlorides or anhydrides because they're too reactive. Instead, it uses the thioester, which is really good at addition and substitution reactions, nucleophilic acyl substitution reactions, but at the same time is stable enough to last for quite a long time in water. The synthesis of fatty acids begins with acetyl-CoA. CoA is a large group. CoA stands for coenzyme A, and it's just a long chain of other things with a sulfur with an SH group on the end of it. So it's a thiol. And like the generic thiol we listed above, the negatively charged sulfur thiolate for CoA is a good leaving group. So nature begins with this thioester and does what's called a trans-thioesterification reaction, in which this acyl carrier protein, which is sulfur at the end of this acyl carrier protein, attacks the carbonyl carbon to give a tetrahedral intermediate, and then the CoA thiolate is kicked off. This is nucleophilic acyl substitution, and it was, I think, problem 1 on your exam asked you to deal with the mechanism for this. I won't draw that mechanism in currently, but and I'll use ACP to represent the acyl carrier protein. But the point is, we've just transferred acetyl-CoA, the acetyl group, onto this acyl carrier protein. And the function of the acyl carrier protein is to act sort of as a crane to deliver this acetyl group, these two carbons with the carbonyl here, to various subunits of the fatty acid synthase complex in order to make the bonds that are required to extend the two carbons of this acetyl group to a much longer chain. All right, so once we've loaded acetyl-CoA onto the acyl carrier protein, there's another step, and this is the Claisen step. Now, in a Claisen reaction, we would use an enolate, and we would have that nucleophile attack the carbonyl carbon to give a tetrahedral intermediate, which would look like this. And then electrons would kick down and kick off the leaving group, which is the negatively charged thiolate. And that would give you, as a product, this new beta-keto thioester. Notice, as before, here was our enolate nucleophile, here was our electrophile. The enolate nucleophile ends up here. The electrophile ends up, oops, I wanted purple. The electrophile ends up here. And notice we've linked two carbons together. Now, it turns out nature makes this enolate in sort of a creative way. As you know, the pH of many areas in biology, cytosol, extracellular matrix, serum is around 7.5, 7.4. And at pH 7.4, you would expect not to see very much of this enolate at all. And so what nature does is it uses a so-called masked enolate. By masked, I mean it's a molecule that could be an enolate that's primed to become an enolate at the opportune moment. So enter this molecule malonyl-CoA. Nature actually makes this from acetyl-CoA and carbon dioxide, though the carbon dioxide won't end up in our product. And we won't worry about this making of acetyl-CoA from, or making a malonyl-CoA starting with acetyl-CoA and CO2. But notice malonyl-CoA has the pattern of being a beta keto acid, which means it's primed for decarboxylation. And what happens when we decarboxylate a beta keto acid? Electrons kick here and then end up on the alpha carbon. That's where we get our enolate from. And of course, CO2 bubbles off, gets dissolved in your blood, and you exhale it from your lungs, but it's likely this loss of CO2 that provides the thermodynamic driving force that makes making the enolate downhill. Okay, so we decarboxylate malonyl-CoA to get this enolate, and then that we end up with this beta keto thioester. Now, ultimately, a long chain fatty acid is going to have 14, 16, or 18 different carbons. So we've got a long way to go before we get from this beta keto thioester to the final fatty acid product. But notice that, that the number of carbons in the fatty acid product is even. That's because this fatty acid product is generated from a process that adds one 2-carbon unit to another 2-carbon unit. So fatty acids almost always, that are natural, almost always have even numbers of carbons. There are a few other reactions that occur at this point. We won't talk about them in any detail now. We'll learn about them later and draw mechanisms later. We're going to reduce the ketone to an alcohol with NADH. We're going to eliminate OH minus to give the alpha beta unsaturated molecule. And then we're going to reduce to the alkane using FADH2. So when we reduce the ketone, it's going to look like this. When we eliminate to get that alpha beta unsaturated thioester, it's going to look like this. And once we reduce the double bond in the alpha beta unsaturated carbonyl compound, we'll have this longer chain thioester, in which both of these 2-carbon units came ultimately from acetyl-CoA. Right. And so once we get to this stage where we've reduced the chain to a hydrocarbon, we can load this thioester back onto the acyl carrier protein, and then a second equivalent of enolate can come in and add another 2-carbon unit to our long chain, such that over time we can elongate the hydrocarbon chain to have many different 2-carbon subunits. I guess we'll sort of run out of colors if we keep going, huh? Each of these would have been delivered by acetyl-CoA. All right. So that's the classic example of the Claisen reaction in biology. All right. Next thing we need to talk about is conjugate addition. We've seen conjugate addition before. We either called it conjugate addition or 1,4 addition. The previous example was to take an alpha beta unsaturated carbonyl compound like this, and then we used a cuprate, such as this diphenyl cuprate, to deliver a nucleophile to the beta carbon of an alpha beta unsaturated carbonyl compound. The reason we could do that is because if we make the new bond between our nucleophile and the beta carbon, the electrons in the alpha beta carbon-carbon pi bond can move over onto the alpha carbon where they are stabilized by resonance. And then in a subsequent step, we can pick up a proton. That usually happens during aqueous workup to get the product in which we have a nucleophile having been attached to the beta carbon. So we're going to introduce a new reaction called the Michael reaction, or the Michael addition reaction. But this is really just conjugate addition of an enolate to an alpha-beta unsaturated carbonyl compound. So how might this work? Well, let me take this aldehyde and then maybe this aldehyde, and let's do the conjugate addition reaction. First, OH minus would remove a proton from the aldehyde to give you an enolate. We can't form an enolate from this alpha-beta unsaturated carbonyl compound because the alpha proton is not lined up with the carbon-oxygen pi star, and therefore the conjugate base would not be stabilized by resonance. Now at this stage, for conjugate addition, we will attack the beta carbon. Now, I think some of you are likely to ask, how do I know that I attack the beta carbon as in the Michael reaction instead of attacking the carbonyl carbon as we would in the Aldol reaction? And the answer is, I'm not sure you necessarily would in a predict the product sense. This reaction is most useful. I mean, understanding the mechanism of this reaction is useful in answering sort of the question, if this is my starting point and then I give you a product, how did you get from starting material to product? And can you push arrows that show that process? Another thing is, it's a decent rule of thumb that if one of your reactive partners is an alpha-beta unsaturated carbonyl compound, that an enolate's going to react with the beta carbon. Of course, in the regular aldol reaction, there is no alpha-beta unsaturated carbonyl carbon, so the only place that can be alpha-beta unsaturated partner, so the only thing that can be attacked is the carbonyl carbon. All right, let's show the product of that. I'm going to redraw this part of the molecule here with a negative charge on the alpha carbon. The new bond is here. And then here is the part from my enolate. So I think above in the Aldol reaction, we used orange for the nucleophile and purple for the electrophile. So here is the portion that comes from my nucleophile. Here's the portion that comes from my electrophile. At this stage, we can show the molecule getting protonated on the alpha carbon to give you the product, which is the following aldehyde. The following dialdehyde. Now, you can learn to recognize this type of molecule as the product of a Michael reaction. And one way to do that is to start on one end and call it the carbonyl carbon, alpha carbon, beta carbon, gamma carbon, and then realize that the gamma carbon, the purple gamma carbon, is also orange alpha carbon. In other words, this carbon here is alpha to the orange carbonyl, but gamma to the purple carbonyl. When you have that pattern, you could have made this bond between beta and gamma carbons via the Michael reaction. Another perhaps easier way is just to start numbering with one of the carbonyls, 1, 2, 3, 4, 5, and to realize that a 1,5 dicarbonyl compound is something you could have made via the Michael reaction. Okay, so be able to, given a Michael reaction starting material and a Michael reaction product, be able to draw the mechanism. Given an alpha beta unsaturated carbonyl compound and an enolate or a molecule that could form an enolate, be able to draw the Michael products. Okay, the last thing we need to talk about is perhaps the toughest mechanism you'll encounter in 352. It has a name. It's named after a Nobel laureate whose last name was Robinson, and it's called the Robinson Annulation. Of course, annulation means ring formation. So the Robinson Annulation is a reaction that makes a ring. It has the same root as annual, or in Spanish, the word for ring is anillo, same sort of basic root, forming a ring, the Robinson Annulation. But you'll be far more successful at this if you don't think of this as its own thing. It's just a Michael reaction followed by an intramolecular aldol of a 1,5-dicarbonyl, which is a Michael product, right? So let me show you an example of this. You start with a ketone or a carbonyl compound that you can make an enolate from, and then an alpha beta unsaturated carbonyl compound. Here's going to be our electrophile, and here's going to be our nucleophile. And we're going to use just simple base conditions to do this reaction. We will begin by removing the proton on the molecule that we want to make an enolate of. Now, in class today, I got the question, how do I know that the base removes the proton on the orange molecule, alpha to the orange carbonyl, versus this proton that's alpha, this carbon that's alpha to the purple carbonyl? The answer is you could definitely remove that alpha proton, but its removal and anything that might happen with that enolate would lead to not the most stable product. This process is an equilibrium process, and it's going to lead to the most stable product, which in the end is going to look like this. And this portion will have come from our alpha beta unsaturated carbonyl compound, and this portion will have come from our the molecule we made an enolate out of. And we ultimately will have made these 3 bonds, 2 sigma bonds and 1 pi bond. So let's draw how this happens. We first form the enolate. We make a very small amount of it. I will draw that resonance structure. Then we're going to have the alpha carbon of the enolate attack the beta carbon of the alpha beta unsaturated carbonyl compound. In so doing, we'll break the pi bond between beta and alpha carbons. Excuse me. And this will create a new bond between orange alpha carbon and purple alpha carbon. And we'll put a negative charge on purple, a bond between orange alpha carbon and purple beta carbon. We'll label everything. Then we will pick up a proton on purple alpha carbon, probably from water. And that will give us the following 1,5-dicarbonyl compound. Again, carbonyl carbon, alpha, beta, gamma, and the gamma proton is alpha to another carbonyl, the gamma carbon's alpha to another carbonyl. Alternatively, the carbonyls are on atoms 1 and 5, so it's a 1,5-dicarbonyl compound. Okay, that's the Michael reaction. Second will be the intramolecular aldol of this alpha beta unsaturated carbonyl compound. Now, this example happens to be lovely because our 1,5-dicarbonyl compound is symmetrical. These two ketones are now identical, so it doesn't actually matter which alpha protons get removed. If we look closely, we'll see we have two different kinds of alpha protons. We have one here and one here. If we made an enolate at this more substituted alpha carbon, that cyclization reaction would involve a 1, 2, 3, 4-membered ring, whereas if we make this less substituted enolate, the cyclization reaction would involve a 1, 2, 3, 4, 5, 6-membered ring. So it's actually way better for us to remove the alpha proton. We're still in basic aqueous solution for this, so it's reasonable for OH- to remove that alpha proton. Again, the driving force, all of these are equilibrium steps, so the driving force is going to be the stability of the product relative to the starting materials. So this is the new bond that we made. Oops, don't like those methyl groups. Here are the two methyl groups. Here is the enolate. I'm going to continue to highlight the different parts of this molecule so we can keep track of what goes where. Now would be a good time to number atoms starting with the alpha carbon and that's going to attack and then ending with the carbonyl carbon. It's a 6-membered ring, so we attack the carbonyl carbon to get a tetrahedral intermediate. I guess I don't like what I did with that arrow. Let me try again. We attack carbon 6. We know we made a 6-membered ring, so at this point what you do is you draw a hexagon and then you start numbering the atoms of the ring. 1, 2, 3, 4, 5, and 6. The new bond that we made is between 1 and 6. There's also the bond we made between 5 and 4. Let's see, carbon 4 should have 2 methyl groups on it. Carbon 2 should have a ketone. And carbon 6 ought to have a methyl group and a negatively charged oxygen, which will get protonated by water to give us an aldol product, which is a beta hydroxycarbonyl compound. And then to get to our final product, we're going to do that elimination reaction at the end of the aldol. This is beta hydroxycarbonyl compound. We'll have OH- remove this proton that's alpha to the carbonyl and adjacent to the hydroxide. That will give us the following enolate. whereupon electrons on the alpha carbon can kick down, and the negatively charged carbon is reactive enough to kick off a negatively charged oxygen as a leaving group. And here are the new bonds that we made. And in case you lost track, here are the atoms that were in our alpha beta unsaturated starting material, and those were the atoms that were in the ketone. And so we have, out of this process, made 3 bonds. We made a sigma bond, and that sigma bond here we made via the Michael reaction. That was step 1. And then the sigma bond here we made, let's be more specific, that sigma bond we made via the Michael reaction. That sigma bond there we made via the Aldol, and then the pi bond we made via elimination of the beta hydroxy carbonyl compound to the alpha beta unsaturated carbonyl compound. So this is the product of a Robinson annulation. It itself is an alpha beta unsaturated carbonyl compound, but it's in the context of a 6-membered ring. The product of this 2-reaction series is called a cyclohexene-one. So if you see a cyclohexene-one, you could have made this via the Robinson annulation, which is first a Michael reaction followed by an intramolecular aldol reaction. And we'll finish there for today.